Okay, so we will continue on fractals, right. So, last time we were talking about fractals. In fact, we looked at geometric fractals, right. So, just to recapitulate some of the properties and details we discussed about fractals. So, one of the thing is that they exhibit infinite details, right. So, which basically means that if I try to zoom in to the fractal structure, I keep finding the details. So, the amount of detail which are inside the structure, truly speaking, they are at infinite level. So, you keep zooming in, you keep finding details in it. So, for the purpose of creation of these fractals, we put a limit to it because of the resources we have, computational space and whatever. So, we cannot do this at infinite level. And the other important property they exhibit is the self similarity. So, the self similarity property is again referring to the situation where one is trying to zoom in to the structure. You observe some scaled copy of the same structure when you zoom in. Right. So, there is a self similarity from what it was originally as a structure and what you keep finding as in the details. So, in fact, these two characteristics one when observes also finds in many of the natural phenomena. Right. For instance, you take a view of a mountain and you try to approach the mountain, zoom in. So, first of all you find lots of details coming out, and the second thing is the kind of structure you observe has some similarity to the overall structure. So, that is self similarity. So, many of these natural phenomena also show these characteristics. So, that is one of the reasons fractals are chosen for modeling natural phenomena. That was the motivation. So, if we go back and look at the process of their generation, so it turns out that it is a recursive procedure where you start from some initial state and you consider a transformation function, right, which could be a transformation in terms of a geometrical pattern or some other transformation, and you keep applying that transformation function. So, there is a recursive application, successive application of the same thing. So, it is a recursive procedure which is what adds the details into the structure. Right. So, the other observation we had, which was particular in the case of geometric fractals, that the process of generation is deterministic. You take a copy of the transformation and then reapply that, the same transformation. So, and it is deterministic, which in fact renders in these geometrical fractals the regularity in what the pattern gives you. Though these fractals demonstrate irregularity in their structure, but the way these get applied show a regularity in that pattern. So, there is a regularity in the irregularity. Right. So, that is because of the fact that they are deterministic in the process of the generation. And we also observed that they have a dimension like what we observe in Euclidean geometry, but this dimension is referred to as fractal dimension because of the fact that this could be fractional as a number. So, you can have a fractal dimension like 1.26, 1.89 and so on. And we also observed the effect of this fractal dimension in some sense captures the roughness of the structure which we obtain, the amount of roughness let us say, and also a self-filling characteristic. Right. For instance, we observed that when a fractal dimension goes from 1 to 2, so you can actually have a fractal dimension of 2 for a curve. Then the property of self-fillingness is observed. So, when the fractal dimension is 2, the whole area where it gets applied, it sort of self-fills, which intuitively matches to the dimension what we observe as a Euclidean dimension of 2 for a planar structure. Right. So, these are some of the characteristics which we observed in the case of geometrical fractals. So, just to give you what was happening. So, again let us say looking back to the construction of von Koch curve. So, you have a pattern of this kind. So, we start from a state which was say a straight line, and this is the transformation which is applied. So, that is the transformation we are referring to as f, and then you again apply this transformation to each of these segments. So, this is what is happening, that is what the recursive procedure is, and so on. So, ultimately you get a rough pattern structure, right. This is the von Koch curve. So, now the problem with them is, as we looked at, is because of the nature of their generation which is deterministic, they exhibit the self similarity property in exact form. So, they are exactly self similar structures, right. Now, when we are referring to them as procedures for constructing natural phenomena, where we observe that there is no deterministic pattern, but in fact there is a randomness into whatever we observe, then there is a modification to this process where randomness is introduced. So, the fractals which have some randomness to it are referred to as random fractals. Okay. So, the whole idea is that the process of generation would now have some randomness in it. Okay. Which in turn renders a self similarity, but in a statistical form. Right. So, when you zoom in a fractal structure which is randomly, which has randomness in it, then what you observe that the zoom in structure is seemingly similar to the original structure, not exactly similar. Okay, so, that is what we mean by statistical self similarity. So, there are number of ways in which these random fractals can be generated, and that is what we are going to look at. In fact, one of the features of the process of generation you observe is involving some sort of a subdivision mechanism. See, adding details in some sense a method of subdivision. Then what you do at the level of subdivision is something different, but as a process you are doing some sort of a subdivision, even when we are generating these these geometric fractals. So, that is what we are going to look at. What are the various ways one can think of as a process of subdivision, which in turn gives you a generating approach. Fine. Okay. So, let us see the process of generation, and one of the ways in which one can think of generating these random fractals is a midpoint subdivision. So, let us consider an example where we are interested in creating fractal curves. Right. So, again one can start from a line A to B, which is like an initiator to the fractal, and you want to add details to this line similarly as we did in geometric fractals. So, when we are saying that it is a midpoint subdivision, so the idea here is that we would consider the midpoint of this line and do an action to that. Okay, that is why we call this as a midpoint subdivision. So, what do? We actually take this midpoint, which is at M, displace it, let us say to the point C. So, this AB line, initial AB line, now is transformed to two segments, AC and BC. Fine. Now, clearly there are issues concerning as to how much do you displace, right? What is the magnitude of MC? And the other issue is in what direction do you displace? These are the two basic issues, right? So, any suggestions to this? When we are displacing this M to C, remember that this process has to continue. Next time what will happen is I will consider this as a segment, take the midpoint here, do a displacement of that. Similarly, this segment, take a midpoint of this and displace it. So, at every level I am performing this process of subdivision and a displacement of that midpoint for that level. So, at various level this issue would arise. How much do I displace and in what direction do I displace? So, one of the thing which needs to be looked at is that the displacement has to capture the level or the scale where I am, right. So, at this level this is the displacement because of the fact that this is the scaling, this is the initial length I had. So, this has to in some sense scale with this. Similarly, when I do a displacement here, this has to scale with this. And the second thing is the direction. So, direction could be, some suggest that you could actually do this displacement only in one direction, which is in 2D if considered this as x and this is y, then this is y direction, or it could be the direction of the normal of this segment. So, here it will be normal, here it will be normal here. The other, let us say, parameter to the generation is the flipping of it. Remember, we could actually go positive offset, we can also go negative offset. So, that is also additional parameter, something like a flipping what we used in the construction of dragon. So, these are the various parameters one can play with. So maybe at the end of the whole thing we get something like this. Okay. So, this seems some of interest if you are trying to use them for modeling some natural phenomena, for instance coastal line, unlike von Koch curve, which was extremely regular structure. Fine. So, I have an example of something which could be a coastal line, but the authenticity is not guaranteed. So, let us say you consider having a coastal line of this, right, where what you have done is you have supplied an initial structure, right, which gives you a gross shape. So, it is like the initiator where you want to start the generation of fractal curves, and then apply this random fractal generation on the initiator. So, you may get this, right. So, clearly this should not be confused with the exact GIS data of Indian map. But let us say if you are doing a simulation or doing some synthesis, computer generated synthesis. So, this is a fairly acceptable approximation, right. Okay. So, this was concerning the curves. A similar idea can be now used for surfaces. So, let us say we are talking of surfaces. So, in fact, there are number of ways we can look at the process of subdivision again. So, let us say you have an initiator of the kind where you divide or you construct the surface as collection of triangles, right. So, at some iteration, say n, you have a configuration like this. So, there is this triangle, there is another triangle here, okay, and you have the data for these, positional data of these. Okay. Now, there is a type of triangle edge subdivision where you do something very similar to what you did in the case of curve, where you obtain the midpoint of each of the edges in the triangle. So, this is the midpoint, this is the midpoint, this is the midpoint, and so on. So, that becomes your next level of surface, and then appropriately do the construction of triangles using those points, right. So, basically what I mean is this. So, the next iteration, let us say n plus 1, has got these additional points which are nothing but the midpoints of the individual edges of the triangle which are there, and then you have these as new set of triangles. And this can be repetitively done. From this iteration you can go to the next iteration where you subdivide each of the edges here and then again do a construction of set of triangles. Fine. So, let us say if we are doing this, so this is what is happening in a topological fashion, how these triangles and the points are being added. Again, at a surface construction level, you have, let us say this is the triangle to start with. This is the initial triangle. This is the these are the midpoints you had. So, because of these points, now this whole triangle becomes in 4 triangles. So, this is the topology of triangles which have been constructed. Now, you have to also do the height assignment, right. That is where the perturbation to the surface would come, right. So, what you are going to do, you are going to displace this point to a certain height, you are going to displace this point to a certain height, you are going to displace this point to a certain height, something very similar to what was done in curves, right. So, you have this height and this height. So, the new surface is this triangle, this triangle, this triangle and this triangle. Right. So, again there are issues. What are the issues?
So, the direction, the amount by which you displace in the y direction.
Yeah. So, one of the thing is the direction where you in which you displace these points. Okay. So, let us see the issues. What I am trying to refer here is, again one of them is the amount of displacement. So, amount of displacement is relevant. Let us say we go to the next level where we take this triangle and we take this triangle. So, there will be a midpoint here somewhere which would be shared between this and this, right. So, the amount by which I displace for this set of triangles has to be the same as for this, otherwise there is going to be an inconsistency. And when I am using the randomness, which is primarily obtained by some random number generator, one has to be consistent in getting these random numbers or the random heights for the two adjoining triangles, otherwise I would end up getting inconsistency. So, one may have to relate, let us say if you are using some seed based generation of random, then one has to maybe use the indices of the edge to determine the seed. It has to associate to the edge, right, so that you are consistent in the height you assign. So, similarly the direction of the displacement. So, once again if I have the midpoint here which is being shared and I displace this, let us say along the normal of this triangle and the other one along the normal of this triangle, then I am going to have a rupture, I will get a hole. Okay. So, there also you require consistency. So, one has to address the issue of consistency whenever you are doing this, both in terms of setting the amount of displacement and choosing the direction in which you displace. Fine. Okay. So, let us see some of the results. So, if you consider this as your base triangle, so this is at a level 2. So, 0 level is the base triangle, level 1 when you have 4 triangles and the level 2 is after that. So, this is the level 2 and then this is level 4 and so on. So, at the end you get something like this. It is not too bad, that is all I can say, right. It does not still look like a mountain, but it is okay. Right. So, one of the issues actually you observe here, and that is the question I am going to ask you, is that what is the rendering or let us say shading model one should be using for rendering fractals. You understood the question? What is the shading model one should be using for rendering fractals? So, would you be doing Fonck shading, or would you be doing growth shading, or would you be doing flat shading? Any idea? Okay, so let us say I give you the answer. The answer is that you should be using flat shading. Tell me why. Okay, not getting anywhere, huh? Say you were using here growth shading or Fonck shading. What kind of result you would have had?
So we want
Yes.
to see this difference, the sharp edge which is coming between the two subtriangles.
See, if we were to use growth shading and Fonck shading, what would that have done? In fact, smoothened the rendering. That's what it does, thereby removing the details. So, the whole purpose is lost. At one point you are trying to add details through subdivision, and when it comes to rendering them you just do the reverse process. Does not work. So, you would be actually using flat shading. Okay, so next, yeah, there is another. This is slightly better result than the previous one. So, perhaps previous was one of those the kind you would have generated in your assignment, but this is somebody else has done it. So, so here this was the base triangle, you can see that, right? And then these are all the perturbations added as this height during the subdivision. And what has been done is that this zero height, or let us say the height at the base, is given a blue color, something like giving you an impression of water, and again in fact when you change this height you can vary the color. So, there could be different gradation of colors, could be green to brown to whatever. Right. So, this looks reasonable. Okay. Now, in fact, there is okay. Let's talk about some other ways of doing this subdivision. So, one was this triangle edge. There is another way which you can use for subdivision is the diamond square method. What is diamond square method? Let us say this is the configuration you have at an iteration n. Right. So, these are the points given to you. Now, in the case of diamond square subdivision, this is what happens topologically. You obtain this point, which is the average of these 4 points. Similarly, you obtain this point, which is the average of these 4 points. This point average of these 4 points, and this point as average of these 4 points. So, there is a middle point for this square, which is the average of the corner points. And then you have this point, which is obtained from these 2 points. You have this point, which is obtained from these points. You have this point, which is obtained from these points, and so on. Right. So, what you sort of construct this shape on the top of this shape, right. So, these are sort of diamonds on the top of squares. So, that is why they are called as diamond square subdivision. Right. So, this is one way of, another way of doing a subdivision. See, one of the thing which is some sort of common between this and the triangle H subdivision, that you end up getting points onto the edges here. Right. So, there is a point here, then there is a point here, there is a point here. Now, to retain the consistency which we had discussed, what might happen is that you may have some sort of an artificial edge getting appeared in the final structure. You see what I am saying? To maintain the consistency, because of the points which are being now created along this edge, you would see some lining on the final structure. Right. So, that is in some sense an artifact which may be there in the case of diamond square subdivision and also in the case of triangle edge subdivision. Okay. So, that is also referred to as crease effect. It is an artificial crease which is being formed, right, at the edge. So, in order to avoid this, there is another scheme of subdivision which is called as square subdivision. Okay. So, here what is done is you have again these points, let us say at an iteration n. So, what happens in the next iteration, that is what we are going to look at. So, this is what happens. Here we create these 4 points within this square, another 4 points within this square, and so on. Right. So, basically this square is in some sense getting replaced by this square, and so on, and these 2 squares are again joined. So, there is a square here, square here, square here. So, from squares you get squares. It's structurally. Now, how do you get this point? That is the question we should answer. So, this in fact is obtained using bilinear interpolation. So, let us say these are the 4 corner points we have, and we are trying to locate this point. Okay. Now, let us say I just enumerate that as 0 0, 1 0, 1 1, 0 1. Okay. So, this particular point is located at 1 by 3, right, and this particular point is located at 2 by 3, and so on. So, if I perform a bilinear interpolation, see, one pass in this direction, another pass in this direction. So, this point can be located in some sense from the weights which are shown here, right, like the weight of 9, 3, 3, 1, which are nothing but the coefficients, weight coefficients which one needs to apply to the respective point. So, this point is basically obtained as 9 times this point, 3 times this point, 3 times this point, and 1 time this point. Okay. Which you can further normalize, divide the whole thing by 16. Right. So, these are nothing but the, and in some sense it is all telling you the proximity of this point with respect to the 4 corner points, which is what happens in bilinear interpolation anyways. Right. So, similarly the corresponding weights would get determined for this point which you are trying to obtain here, and this point and this point. So, each of these 4 points now can be computed using bilinear interpolation from the corner points of the square. Fine. And once you have obtained this point, all the points of the square, then you have obtained a new configuration for the iteration n plus 1. Now, this can be again repeated. And if you want to preserve these boundaries, because what is happening is, in some sense I have now from this boundary I have reduced the boundary to these, right, and in further iteration I would come here somewhere, right. So, but if you want to preserve these boundaries, then you have to do something extra within this region. So, you can obtain extra points which would locate points here, locate point here, and so on. So, you have extra squares for the boundary cases. Fine. So, so in fact, let us say if I were to use this process of repetitive bilinear interpolation to a curve or to a surface in this fashion, like a subdivision, what is the limiting surface we have? See, if let us say if I were to use some sort of a midpoint subdivision, just take an example of a curve. Okay, maybe I can show it from here. So, what I mean to say is, this is the situation to start with. Now, I am obtaining a point here and obtaining a point here, which is the midpoint of the two. Right. Now, in some sense I have, so let us say I preserve the boundaries also. So, in some sense I have new set of points like this. Again I can do the same thing. So, what happens is this, right. So, what is the limiting curve I have? This is a subdivision we have seen, right, even of a Bezier curve. It's a quadratic curve, right? It's a Bezier quadratic curve, isn't it? We keep subdividing it, and then now here what we are doing is we are actually perturbing them. Right, so this is topologically, this is what is happening, but then you are perturbing the heights, and that is what will create a structure like a terrain or a landscape. But this actually does not give you the artifact of creasing, because every time you compute these new points, so these points are not aligned to one of the edges, right. So, this removes the artifact of creasing. Fine. So, this was due to Given Miller, I think introduced in SIGGRAPH 86 or so.
But how do we ensure consistency in this case?
See, the consistency is, so what I am doing is I am computing the height of this from these guys. Similarly, height for this with the same weight structure. So, there is no issue there. Is it fine? So, it's basically 1 over 16 times height of this, 3 over 16 times height of this, 9 over 16 times height of this, 3 over 16 times height of this. So, there is no issue of consistency here. Okay. So, now some of the applications, well, we have seen examples of coastlines, we have seen example of landscape. In fact, this is a much better example now, right, which even has some fogginess to the atmosphere, right. You can also do clouds in a similar manner, where you in the case of cloud, what is it that you need to change is the opacity, right. It is the opacity which would determine the thickness of the cloud, right. You can even do candies, and in fact, the slides which I have circulated contains an example of candies. It is not candies, the internal of the candy, not the candy to eat, but the cover of the candy, which you can generate using a similar process. Also stones and many other things, right, plants, trees, which we have already seen. Okay. So, now the next, so these were random fractals, and we can see the relevance of these random fractals towards the modeling of natural phenomena. There is another kind of fractals which are also referred as algebraic fractals. So, you might have heard Mandelbrot's set or Mandelbrot's function, which is again some sort of a generating or a transformation function, z is equal to z square plus c, where z and c both are complex, they are both complex numbers. Okay. So, the idea here is, when we are saying algebraic fractals, we are basically doing a visualization of this function, right, how this function iterates. So, for that there is a very simple algorithm. So, consider C to be, let us say, the point on the region you want to display. The fact that these are complex numbers, they can be written as something like x plus I y, right, which is the position in 2 dimensions, right. So, if I consider C to be the point in question for the region to be displayed and z naught given as an initial value to z. So, this is the function which I am going to use. So, there has to be some initial value of z, which I call it as z naught. Then all what is happening is the evaluation of this function, which is z n is equal to z n minus 1 square plus c, right. Then what you do is you examine the size of this z n, right. The size could be just the squares of the real part and the imaginary part. So, this is the size. So, what you are basically looking at is some sort of a divergence characteristic of this function, z is equal to z square plus c. So, clearly there is this self squaring which is happening to the function. One would imagine that this function would diverge so, right. But it turns out that there are points they never grow after a certain value, right. That is what actually gets defined as Mandelbrot set. Okay, so, here we are just looking at a mechanism of displaying this process. Okay. So, when we do the evaluation of this size, if the size turns out to be a tolerance defined by you, then you assign a color which is actually a function of this n, which is the iteration count, to this point C in the region. Okay. And if it turns out that it never grows after a certain size, that means you have crossed a certain limit of number of iterations you have assigned for, then again you assign color to that n, which is the limit of your iterations, right. So, this would give you the set of those points which stop growing after a certain number of iterations, right. So, that is what is the entire algorithm is all. Okay. So, the kind of structures you would observe is something like this. So, this is the start where you have a region starting from, let us say, minus 0.5 to minus 1.25 to 2 to 1.25. So, there is a radius of 2.5 region, okay, and you obtain something like this. So, and these yellow points are the points which do not grow after a certain number of iterations. Okay. And that is what the Mandelbrot set is. Now, the interesting point is, and that is where we would like to see this, the similarity of these fractals, the algebraic fractals vis-a-vis the other fractals we have observed, is that if you zoom in to the structure, see, if you take a small part here and try to zoom in here, this is what you obtain. Okay. So, by zoom in, what we mean is that you take a small region here, increase the resolution of your computation for the region C you define, and obtain this. So, this is what you get after zooming, and what you observe is that there are similar structures like this, which are of the similar shape which you had obtained at the first level from where you have zoomed. And again you can keep doing this process of zooming in. So, again you find details. So, there is infinite details to the structure, that is one observation. which is what is shared by the other fractals, and also there is a recurrence or reappearance of a similar structure which you had started with. So, there is this property of self similarity. Okay. So, for the purpose of looking at as a process of generating these patterns and structures, they are in the same category, right. So, that is what we are also looking at. We are perhaps ignoring the mathematics of this function, right. Okay. So, in fact, there are people who have attempted looking at the generalization of this, where z is actually coming as z to the alpha plus c. Rather taking a z square plus c, you consider some power of z, right, and this alpha could be an integer, it could be a real, it could be positive or it could be negative. Okay. And interesting patterns can be generated using this. Okay. And one characteristic which is observed is that if you define L as a lobe structure. So, let me go back and say that this is one lobe structure. Okay, if I say that this is one lobe structure, then the number of these lobe structure is basically given as the floor of absolute value of alpha minus 1. Okay, so, when I had alpha to be 2, then the number of structures I had 1. If I consider alpha to be 3, then the number of lobe structures is going to be 2, and so on. In the slides which I had circulated around, you can see there are patterns where a different alpha is considered other than 2, and you have these various lobe structures, right. And there is another interesting observation is that even the fractional part signifies some sort of a beginning of the growth of a small lobe structure, right, which is like a baby lobe structure. Okay, so people have tried other functions also. So, this is the book you have, Beauty of Fractals, full of such structures. So, those of you who want to have a look at it can take it and see it. So, just to give you the idea of this, I think the resolution is not so good. So, what do I mean by the these lobes are somewhere here. So, this is like I am calling one lobe, okay, this is another lobe, and so on. So, for alpha is equal to 10, you would have 9 such structures, right. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And even in the case of negative number, so this is alpha is minus 10, okay, and this is what I am referring to as a lobe structure. So, there will be 11 of such. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So, anyway, see, we are not actually looking at the implication of this number in terms of the mathematics behind it. We are just trying to display them. So, there are in fact very interesting properties with respect to what happens mathematically to these. So, one can take other complex functions and see this. and clearly this would not happen to all structures. See, there are only certain structures which would exhibit the property of self similarity and details inside. Okay, so there is a class of functions which would give you this, right. Okay, so let us stop here. Next time we will talk on something else. Maybe we will start animation. we have been talking about various issues in computer graphics, primarily modeling, rendering, right. So, today we are going to start another aspect which is also very important in computer graphics, which is animation, right. So, much of what we do through computer animation in fact has been inspired from conventional animation, right. So, if you just look at the term animation, right. So, it has origin from a Greek word animos and Roman anima, right, which basically means to bring to life, right. So, there is a sense of evolution over time, right. So, things are changing over time, that is what we capture through animation. So, conventional animation has been there for a long time, right. So, and the primary concern there of animation techniques has been to create this illusion of movement, right. So, what are we trying to do is basically have the aspect of movement which could be just an illusion, right, without simulating the motion in its physical sense, right. So, so what it may involve is basically let us say creating photographs, a series of photographs, right, as frames, and then run through those frames over time. Okay, that is the idea behind what happens in conventional animation. So, so this aspect of illusion of life has been used by various commercial setups, even Disney animation, for their productions, right. So, for instance, if you look at what I am trying to show through this illusion of movement. So, if you look at the example here, each of these image which you see here, right, they are in some sense a still photograph, okay, with different poses or different variations, okay. And if I run through all these frames over time, so if I just time stamp them, that this is the first frame, this is the second frame, this is next frame, and so on, what I would obtain a sense of motion, right. And that is what we are saying, that that is an illusion of movement, although each of the frame is actually a snapshot, right. It is a static frame, okay. So, that is what happens in conventional animation, and that has been the practice since its beginning. So, now we are also going to look at how we use computer in conventional animation, right. So, if you look at what we have observed, so animation refers to the process of dynamically generating a series of frames of a set of objects, right, or regions in a scene, right, where each frame is an alteration of the previous frame, right. Now, if you look at the kind of restrictions it may impose, is that one, we are talking about a construction of a frame which is a snapshot, right. So, the notion of real time animation is not there, right, because you are generating a frame and then you collect the series of frames and run over time, okay. And the other thing is that it remains in 2 dimension, right, the kind of example we have seen, okay. So, now if you look at the process which is generally employed in the conventional animation, what do we have? We have a notion of what we call a storyboard, okay. So, the animator who is generating the sequence of animation basically creates these drawings, right, which are in a sense capturing what should be the frame, what are the contents in the frame, right, and how these contents are to be laid in that particular frame, right. So what you are trying to do is you give a pictorial depiction of the frame with the description you want to associate. Okay, that is what we mean by storyboard. Even today, this is an important step when we generate animation films. Okay. So, now then we have a notion of what we call as keyframes. Okay, so, while we are generating these frames, it is perhaps not desirable that you do this for each frame. Okay, so, what you have a notion of that there are certain keyframes in the sequence which require proper description, which require proper content definition, right, and then maybe the other frames would be computed using in betweening of these keyframes. Okay. So, that is the notion of keyframes. So, you choose the important frames. Now, in betweening basically means that how do you get the frames which are between these keyframes which you have defined. Okay. So, that in a way require a technique like interpolation, right. So, you have defined these keyframes and then you may employ an interpolation to be able to compute the in betweens. Okay. Now, once you have done this, then there is a process of painting these frames which you have generated, the entire set of frames, right. So, you are doing a sort of a redraw on a film which could be using acetate cells. Okay. So, basically film where we produce the final animation. Okay. Now, one of the aspects which is very popular in the conventional animation is called as stretch and squash, right. So, it is a very simple idea. Imagine there is a sack with partial flour in it, right, flour in it, and then what you are trying to do is squash and twist and deform that sack to be able to generate various effects. Okay, that is what is illustrated here in this, right. So, this is a completely squashed, this is stretched, this is twisted. Okay. So, all this is showing that you can actually generate various form and shapes using the technique of squash and stretch. Okay. So, this even inspires for a technique which you might use when you are using computer animation. Okay. So, this is one technique, and the one of the aspect which we observe in conventional animation, particularly in 2D cartoon animation, is this stretch and squash, right. Because what we are trying to do is have some caricature, right. The caricature in fact does exaggeration, right. So, you want to exaggerate so that what you are trying to impress upon is believable. Okay. So, the technique of stretch and squash and others are basically for doing this, for having an exaggeration. Okay. So, you can straight away observe that this is some sort of a stretching of this, right. This is some sort of a squashing, same idea, isn't it. So, various expressions in animations can be generated using just the principle of stretch and squash, right. Okay. So, next thing is that let us try to sort of see the other aspects which we are trying to address in computer animation. Okay. So, one thing, as I mentioned, that the conventional animation is primarily image by image animation. You generate every frame. Okay. So, when we are doing image by image animation, there is a notion of you compute a frame, right, when you are using computer animation, you store that frame, right, and then you draw the frame when you need it. Okay. So, this is the 3-step process which is involved in image by image animation, whereas if I want to do a real time animation. So, real time animation basically is a process employing compute the frame and draw it. So, there is no notion of storing it, I compute it and draw it, right. Now, one needs to look at the rate of display which you will require to use, right. So, typically when I am generating an animation, I require, depending on what display standards I have, 30 frames per second or 25 frames per second. Okay. So, this is just to enable that our visual perception does not perceive the discrepancies in the frames or jerks in the frames, the transitions in the frames, right. We just see a seamless sequence of frames, right. Now, if you look at some sort of a characteristics of animations, right, one can see there are 3 primary characteristics which may contribute towards animation, right. So, for instance, I may have spatial characteristics, which basically is saying that there are things like position, orientation, shape, form, which is going to change, right. So, that is what we mean by spatial characteristics of animation. Okay. Similarly, you also have temporal characteristics, right. So, there could be a notion of velocity, there could be a notion of acceleration, right. It is just not that things change, but things change differently with time, right. Similarly, there could also be visual characteristics which contribute, right. So, there could be change in color over time, there could be change in texture and so on, right. So, one can see these as a main 3 characteristics which participate towards contributing animation, right. So, keeping these in mind, let us try to look at the techniques which could be used for animation and what has been used over time historically in computer animation. Okay. So, one method which is the rotoscopy. So, there are various methods and we try to look at in 4 categories these methods. One is rotoscopy, then keyframing, then we have parametric animation and then algorithmic animation. So, this basically covers a spectrum of various techniques which we may have for animation, right. So, let us try to see each one of them in more details. Okay. So, let us see what do we mean by rotoscopy. So, rotoscopy basically implies that you are trying to record or register data for each frame, right. So, when I say data, that means it may imply everything, it involves the geometric description of the scene, it involves the illumination characteristics of the scene and so on. So, everything is recorded. Recorded could also mean that I generate that, right. So, I registered that from some means, right, I acquire them. So, what we are looking at is an approach which is extremely data intensive, right. And if you look at this technique could be useful in particular when I am trying to capture a complex motion, which I may not be able to generate by any other technique. right. And also when I am doing so, it is realistic because I am capturing every frame, right. But if you look at as an animation creativity, it's actually less creative since it's just brute force, right. The only emphasis is that you capture the data which is required for each frame, right. So we observe that this is in a sense a data driven animation. There are lots of data which need to be handled, and many techniques today you might have seen through motion capture could fall in this category, right. So this is one of the earliest technique where every frame was registered or recorded, but nowadays because of the complexity we want to include in the animation, this has again become popular, also because we have the acquisition methods, right. So there are lots of motion capturing ways and methods which we can use these days through sensors of various kinds, right, which can give us the required data, right. And also they are technically challenging because what you need there is the brute force data which is coming perhaps maybe at a much larger speed, right. So the amount of data you get could be noised, right, and what you need may be just a small set of that data, right. So you need to filter that data according to your application, right. So this has again become a sort of a trendy method of animation today. Okay. Now keyframing, as we were talking about what do we mean by keyframe. So the notion of keyframe is very similar to what was seen in conventional animation. Okay. So we have this selected or keyframes which are specified, and then we use some interpolation to compute the intermediate frames, right. And this approach is again, though simple, is very popular and still in use. Okay. So most of the animation softwares have keyframing. Okay. Now one of the limitations which we may observe later is that it actually can cause inconsistency in the result, right, or can give you incorrect results. Okay. So let us see what do we mean by this. So if we just see the formulation of keyframing again, what do I have if I have a timeline here, time axis, which is nothing but in terms of the frames I have. I specify these keyframes as let us say KF1, KF2 and KF3, right, and I compute the frames F1, F2, F3 and so on, which are in between these keyframes, right. So any frame Fi, which is the intermediate frame, which may be reflecting the position of a point or an object, then all we are saying is that this Pi, which is the position of a point or the object for the intermediate frame, is a linear interpolation of the position at P1 and the position at P2. Okay. So linear interpolation is one way of doing the interpolation of keyframes, right. Okay. So now let us see what are the consequences if I use linear interpolation. So if I have linear interpolation, one may have discontinuities, right, discontinuity in terms of the spatial discontinuity, or it could be temporal discontinuity. right. So, in order to address the issue of discontinuity, you may use splines. So, splines are basically ways of interpolating which are higher order interpolations, right, which can give you higher order continuity. Okay. Now, if you look at examples here, so there could be some unrealistic results which we may obtain. So, there is, let us say, an example where I define keyframes at kf1, kf2 and kf3, right. So, it is something trying to simulate that some object or a ball is thrown up and it falls, right. Now, if that is the situation I am trying to animate, right, if I use linear interpolation, this is going to give me a result like this, right. So, these white circles are showing the intermediate positions, right. So, what we observe is that this is not capturing the notion that when I throw a ball, right, it goes with certain acceleration or velocity and it reaches this point, right, it sort of slows down when it reaches the highest point and then again an acceleration starts, right. So, nothing of that sort gets captured here, right. So, when I see the resulting motion which I will get using this interpolation may not be realistic. Okay. Now, similarly, so let us say there is an example of linear interpolation here. So, here the interpolation I have from one frame to another frame, right. So, these are sort of frames which are specified over time, okay, and all I have is a trajectory which is computed using linear interpolation where this object moves. Okay. Now, there also if I use linear interpolation, it causes discontinuity, right. So, wherever a joint is coming, I will see a discontinuity in the path and that would give me some jerky motion, right. So, this, as I said, that could be corrected if I had used a spline curve, right. So, if I had, let us say, used cubic curve interpolation, then I would see a smooth transition over this path, right. So, the path is continuous. Okay. So, this may be more realistic and would not have these jerks or the discontinuities. Okay. Now, again, as we are looking at the issues of interpolation, now one can incorporate, let us say I have used interpolation, but what I want to also capture the notion of that there is a slow start in the beginning and then there is a slow stop, right. So, we call it that slow in, slow out. Okay. So, what is happening is that if I use some function of this form, right, which is a function of a parameter t which I am going to use for interpolation, would give me the impression of slow in, slow out, right. So, I can use a function for my interpolation rather than just using a linear interpolation, right. So, here this interpolation is basically on an attribute which could be a position, which could be anything, right, which is represented through Vs, and V is the attribute of the end frame, and I do the interpolation using this 1 minus Ft Vs times Ft instead of just using T, right. So, now any other function, if I want to use, could be incorporated through FT. Right. So, this was just to have slow in, slow out, but if you want to have some other kind of variation, then you can use that function. Fine. Now, again looking at the problem of interpolation. So, some of these problems which we have looked at, which arise from interpolation, and in particular let us say linear interpolation, we can resolve, right, either using splines or, as I said, these functions for interpolation. Now, there is another issue here. Let us say when we are talking about interpolation, and particularly referring to the interpolation of shapes. Okay. Now, let us say I have an object here for which I have a keyframe 1 at t is equal to 0. So, this object is nothing but a square with vertices at 1, 2, 3, 4. Okay. And this is my another keyframe, let us say at t is equal to 1, kf2, which is again the points 1, 2, 3, 4 a square, right. So, in a sense that this square has now transformed to this square, right. Now, if I apply a simple interpolation technique which I use for keyframe and try to compute what happens to the shape at, let us say t is equal to 0.5, what happens? A dot will come, right. So, the whole shape is distorted, right. So, that is what happens. Okay. This is what the result is. Now, if you compute all the transitions, right, going from keyframe kf1 to keyframe kf2, it will pass through this, right, which would look strange. Okay. And one can actually observe these issues or these problems at many different situations, right. So, now in fact, if somebody observes that it is actually a rotation, right, then perhaps a different method is required to be able to generate again an intermediate frame here, and perhaps using only interpolation, right, but not employing or not using interpolation on the shape or the set of points. Fine. So, these things have to be kept in mind when you do keyframing, right. This is what we mean by inconsistencies which can arise using keyframe animation. Okay. So, an alternative is, which is actually inspired from what we have observed, is to use a parametric animation. Okay. What do we mean by parametric animation? See, if we look at many times in many situations, the animation is caused by a set of parameters. Okay. The shape change or the form change is a consequence in change of some parameters. Okay. So, instead of doing the shape interpolation, you may use interpolation of that parameter. Okay. So, your definition of the animation is in terms of that parameter, right. So, a very obvious example is shown here. So, for instance, what you are doing is you are doing some kind of a motion of an arm or a robo arm, right. So, you have a robo which rotates from here to here, right. So, when this happens, the entire motion can be parameterized by an angle of rotation, isn't it? Now, I can generate animation using interpolation of this parameter. right. So, the benefit is that it obviously requires less data, because I am defining the animation in terms of this, right. I do not need to look at the entire shape. Okay. I have a shape somewhere, right, and the entire animation is then defined in terms of this parameter, which I apply onto this shape, right. So, it is some sort of a transformation which I derive from this parameter and apply to the shape of the object, right. So, that is what we mean by parametric animation. This is particularly relevant, as I gave you an example, motion of articulated structures, right. Now, there is another category of animation which we refer to as algorithmic. Okay. See, many a times we observe certain laws of physics or motion to be the driving force for animation, right. So, in fact, what we are trying to do in animation is to simulate those situations, right, for which we know the law of physics or law of motion. Okay. Then it is perhaps better to do or use that law of motion for creating an animation. Okay. So, a very simple example is shown here. So, let us say you have a motion of projectile. Okay. You throw some kind of an object from a height and it hits the ground. And that is the kind of thing you want to simulate. Now, if you use a simple interpolation, then obviously you may get something like this, right, a dotted line which is shown here. So, that is through a linear interpolation, which is completely wrong, knowing that it is a projectile motion. Okay. So, whereas if I had used the law of motion, right, a simple equation to generate this motion, then I would have got this. So, again this is not a real simulated trajectory which I am showing here. This is some curve which I have drawn using tool of a PowerPoint, right. So, but this is just to indicate that I could compute or do the simulation of this entire projectile motion with the known equation of motion, right. So, I can embed the law of physics or law of motion which is there in the process which I am trying to simulate. Okay. So, this gives you the spectrum of technique which could possibly be used in computer animation, right. So, let me just give you an example which will illustrate you some of the techniques which are used even in the commercial studios. Okay. So, here is an example. Actually, this is an example of you perhaps already know Monster Inc., right, by Pixar. So, Pixar is a animation company. So, this is a Pixar project with Disney, right. So, they have produced this. So, here what you see is that this in a sense gives you various stages which may be required for animation. Okay. So, here for instance, you see the first thing which you need to have is a sketch, right, which could be drawn by the animator, right, which is what gets used in the storyboard. Okay. So, you try to give an expressive depiction of what is there in the frame or in that keyframe, right. Now, correspondingly, well, this does not correspond to this frame though, but then the idea is that you try to do some color coding right, to reflect what are the different colors you may be using for these characters. And in case if you are just using 2D animation, right, then you assign the various colors which you would be using for portions here. Okay. Now, if you have the 3D animation, then you try to build the corresponding 3D models, right, or you already have, let us say, 3D models, and you pose these 3D models according to your sketch, right. So, 3D model basically here for instance are shown through the mesh models, wireframes. Okay. Right. So, this is a character called Sully, I believe, and this is Mike. Okay. So, then this is what your rest of the scene is, the staging of the entire action, right. So, this is the scene building where you put whatever is required. So, do the necessary modeling here. Okay. So, and then you have your illumination. Okay. So, this was wireframe, remember, this was wireframe with the color scheme you might have defined. Now, this is a shaded model, right, where you see the shaded objects onto the scene. Okay. And then you may also have further realism through addition like fur or any other aspect you want to attach. Okay. So, all it is showing is that once you have done this 2D displays of these sketches which capture your storyboard, then you create the necessary environment in 3D, right, and do the animation in 3D. Okay. So, let us see the animation here.
I can't believe it.
Oh, Mike.
I was on TV. God, did you see me? I'm on Metro. Hello? I know. Hey, wasn't I great? Did the whole family see it? It's your mom. What can I say? The camera loves me.
Okay. So there is also some task related to, you have created the visuals, right, then you have to overlay the audio on it, right. So, where you do the production, so there are set of frames which you have created and then you have to overlay the sound on it. Okay. And then since it could be a longer sequence, right, a typical computer generated film may have thousands of frames, right. So, you may need to have necessary infrastructure to be able to compute those frames and store them. Okay. Because typically these animation sequences are not real time. Okay. They are more in the sense of frame by frame philosophy. Okay. So, next time we are going to look at more in details about some of the animation techniques, right. But this gives you an overview as to what are the various aspects in computer animation. Okay. Thank you.